Hey, Psych 2317 class. Welcome to our Unit 3 lecture. We are going to be talking about the normal distribution and probability and percentiles and some things like that. So I'm going to share my screen. We'll review what we talked about in the last lecture, and then we'll move on from there. Slideshow. Okay, so what did we learn last week? We learned about what standardization is, right? We took our raw scores and then we converted those to z-scores, and those were our standardized scores. And then we also were able to convert our z-scores back to our raw scores. Then we used z-scores to compare raw scores from different measurement scales, right? Things that would have been like apples to oranges, we were able to convert those both to watermelons and then compare those two together. So what are we going to do this week? We're going to talk about the normal distribution. We're going to talk about how to compute probabilities with the normal distribution, and we're going to use a SciStat app and z-scores. I guess we're using psychological statistics, but via an app and also our z-scores. So the normal or Gaussian distribution. So it's a probability distribution. It's a graph that expresses the likelihood of obtaining all of the possible measurements that make sense in a given context. So I've been talking about that normal distribution or that bell curve, just touching on it the past couple of lectures. And so we can use that to give us probability. So the normal distribution is a probability distribution that applies to a whole bunch of different types of real world data. SAT, ACT scores, IQ scores, height, weight. This is a stats course for psychological science majors. And so really we're mostly talking about scores because that's what we're doing as psychological researchers, right? We're giving some sort of assessment to a sample of our population, and then we're trying to see what that data tells us. And so for the most part, we're just going to be talking about scores. That might not be true in other statistics courses, but for psychological sciences, that's what we are typically referring to. So the normal distribution has a bunch of universal qualities that make it really useful for making inferences and then making predictions about data, right? Because again, that's what we're doing as psychologists or as researchers, right? We're trying to do this study so that we can then maybe predict this would continue to happen in the future if these qualifiers were met or these conditions were right. So some facts that are true about the normal distribution is that it's symmetric, that it can be completely described by the two parameters mean and a standard deviation. So that means the peak. So can I draw on here? Let's see. Look at this. Okay. So mean, and that's here at the peak. That's always the center. And then standard deviation is the width. So if it were more like this, right? It's not as wide. So our standard deviation might be this big, as opposed to here, standard deviation is probably this big. So standard deviation represents the width, and the mean represents the peak. Oh, let's take all that off. So the normal distribution is symmetric, is described by mean and standard deviation, and we know that the area under the curve to the left of mu is exactly 50. Same goes for the area to the right. So half of the scores in a normal distribution are lower than the mean, and half of the scores are higher than the mean. This means that the total area under the curve is equal to 1. So for example, we have this here. So this length, or this width, this is the standard distribution. Standard deviation. I'm sorry, I can't speak. So we have our standard distribution here, our regular bell curve, right? And so here in the center, we have our mean. And then this is our standard deviation. So if it were taller, you can see our standard deviation is not as wide. So the shaded area represents 50%. So here's our mean. So now we have z-score. So you can see the mean is 0 because it's a z-score. And then we go -1, -2, -3 would probably be here-ish. +1, +2, +3 would be here-ish. And so that means that everything over here, all this shaded stuff, that's half. That's half the area. So 50% is here. The area under the curve between mu and our standard deviation and mu plus the standard deviation is approximately 0.68. What does that mean? We can expect that 68% of the scores in a normal distribution fall within one standard deviation of the mean. So that means we can say that 32% of the scores would be 100 minus 68 would fall outside of this range. Minus 16% will be more than one standard deviation below the mean, and 16% will be more than one standard deviation above the mean. The area under the curve between the standard deviation to -2 and +2 is approximately 0.9 or 95%. We can expect that 95% of scores will fall within two standard deviations of the mean. 5% of scores, so 100 minus 95, will fall outside of this range, which means -0.25% will be more than two standard deviations below the mean, and +2.5% will be more than two standard deviations above the mean. So what does that look like? That was a whole lot of words. Look right here. This is what I'm talking about. So in our first slide where we had it shaded, right? We knew that this was 50%. This whole side over here, this is 50%. And this, can I change my color? This. This is the other 50%. So we could look at it that way. 50 and 50. That's half. Well, what about, let me change it back. So it's saying 34% right here is from 0, from our mean to one standard deviation with 34%. Well, that means that 34% also falls within one standard deviation left or negatively or lower. So it's saying that 34 plus 34 is 68%. So 68% of our scores will be right here. Will be one standard deviation above or one standard deviation below. And then that means 14. So this is our second standard deviation. So that's 2. So 34 plus 34 plus 14 plus 14 equals 68, 78, 96. I knew that. I just wanted to make sure because I don't want to write it wrong. 96% of our scores are within two standard deviations from the mean, positive or negative. And then that means 99% of our scores, probably more like 99.7, fall within three standard deviations of the mean. Let's write our other one on here too that I erased. So there's 68%, 96%, and 99, that's a 9% here. So this shaded area is 50% because we have this whole left side, plus 34% because we have this one standard deviation shaded. So that means this shaded area of this standard distribution represents 84%. So for a normal distribution, we're saying ACT scores are an easy one to give as an example. ACT scores are normally distributed with a mean of mu equals 21 and a standard deviation of sigma equals 6. Given the universal qualities of the normal distribution, we could deduce that the most likely ACT score is 21. We could say that 68% of scores should be within one standard deviation of the mean, so that's 6 points. And that means that our lower limit should be 21 minus 6 equals 15, and the upper limit should be 21 plus 6 equals 27. 16% of the scores would be below 15, and 16% of the scores would be above 27, right? Because we just made these limits. This is one standard deviation, and that's our 68%. But then another 16%, right? The second standard deviation. And then our third three standard deviations away, 95% of the scores would be within 2 standard deviations of the mean. So our lower limit would be 21 minus 2 times 6 equals 9, with our upper limit of 21 plus 2 times 6 equals 33. Then lastly, we would know that 2.5% of the scores would be below 9 and 2.5% of the scores would be above 33, right? So we're just taking each limit here, right? Standard deviation, 1 standard deviation here, 2 standard deviations here, and now we're looking at the third. Suppose you scored a 30 on the ACT. Well, I wish you could see this on the curve. I'll just draw over it. So what this slide is saying is that for our ACT, the most likely score is 21, right? Our mean is here, 21, and the standard deviation is 6. So the standard deviation, 21 plus 6 is 27. 27 plus 6 is 34. 34 plus 6 is 40. And then we go lower here. 21 minus 6 is 25. No, 15, sorry. 16. I can't do math while you're staring at me. Where'd my pen go? Where's my pen? 15. And then 9. And then 3. So this, let me get a different color. This is saying 68% of scores should be within 1 standard deviation, 6 points of the mean. So the lower limit would be 15 here, and the upper limit would be 27 here. So it's saying that this is 68% of our scores. And then let me get a different color. 16% of our scores will be below 15 because I'm here. So below and will be above 27 would be here. 95% of my scores would be within 2 standard deviations, so it would be between here and here. So that would be these numbers. And then one more color. How many colors can I use? 2.5% of my scores would be above 33, so 34 and above, or below 9 this way. It's a lot of colors. It's a lot of drawing on the screen, but hopefully that helps you see with all these words where we're talking about on our standard bell curve. So suppose you scored a 30 on the ACT. We could ask 2 equivalent questions. We could ask what proportion of all other test takers scored below your score of 30. Here our answer would be in terms of percentiles. Or we could ask what's the probability that a randomly chosen test taker scores below your score of 30. So we could ask either of those questions, but they're equivalent, right? They're asking the same thing. We're just asking about probability or proportion. So probabilities always range from 0 to 1.0. So the answer has to be noted using a decimal, right? Or a percentage. But our answer will be in decimal form. So an easy way to do this is to go to this website. Dr. Tom Falkenberry, the guy who wrote our textbook, who works here at Tarleton, who taught this class forever very well. He created an app. So you can type in this on your computer, or you can pull out your smartphone and you can just scan them right here. So what we're going to do is go to this. Let me make sure you can see the screen. Where's my new screen? and see which screen you can see. Okay, perfect. Okay, so here you can see this is the website, tomfalconberry.shinyapps.io. So on here, I'm just going to refresh so that it's clear. Um, and then let me move my PowerPoint so I can still see the question and remind you of the question. The question is you score 30 on the ACT. So you want to find out what proportion of all other takers scored below you, and what's the probability that a randomly chosen test taker scored below your score of 30. So we went to this app. So what we need to do is we need to make sure this distribution here is set to normal. There's a T and an F score, but if you haven't taken stats before, you probably don't know what those letters mean. We will be talking about them later on the semester, but not today. Today, just normal. That's all we want. And we know that the mean was 21, right? And the standard deviation is 6. That's what we know about our ACT scores. So what we're going to do here is we're going to click lower tail. And the reason we want to know about it in the lower tail is because we're saying what proportion is less than. Um, and then if we were trying to figure out what proportion is more than, then we would do an upper tail. Sometimes you might need information from both tails, but when you need like two different data points, or the middle, right? That's the opposite of what both tails is. But for this question, we're asking what proportion is less than. So we want to see less than moving this way. And this letter A just gets set to some random number, so erase that. And for us, we're wondering about less than 30. So when we type in 30, you can see here P equals 0.933. That means that the proportion of scores lower than 30 is 93%. 93% of test takers scored below your score of 30. That's it. That's amazing, right? There's this handy little app here. So another way to answer the same question could be using the standard normal distribution table. So if we're using the standard normal distribution table, if I reset this and I refresh, it always sets mean to 0 and standard deviation to 1. So remember that that's what our z-scores are, right? A standard deviation in our standard table, 0 is the mean, and then we have one standard deviation, two standard deviations, right? That's the way that the unit table is normally distributed. So if we did it that way, we know that mu is always 0. We know the standard deviation or sigma is always 1. And we want to convert this. So first we would have to convert our raw score to a z-score, which we did in our last lecture, right? In unit 2, we learned how to do that. So for this, z would equal 30, right? You're saying your score is 30 minus 21 divided by 6 equals 1.5. So if we're going to use this, we need to say 1.5. That's not true. Hold on. Don't do that. Hold on. Normal, mean 0, standard deviation 1. Oh, lower. I was like, that's not working. 1.5. Yes. Make sure it's the lower tail. Make sure you have the right area clicked. Look, P equals 0.93, 93%. Just like that. It's the same answer. But to do that, we needed to have what our z-score was. So let me go back to the PowerPoint so you can see the rest of this. We just did that. Okay, so we wanted to answer the same question using the standard normal distribution. It's mu equals 0, standard deviation equals 1. So we converted our raw score to a z-score. And the reason we used these numbers, let's go back up. So we knew that the most likely score was 21, right? Dun, 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 dun. And we knew that our standard deviation was 6. So that was how we were able to get our, sorry, I'm trying to get the purple off. That's how we were able to get our raw score converted to a z-score and then use the standard unit normal table. That's it. Sounds complicated, but seeing it that way, it was not. And then just real quick, so what you could have done besides using the standard normal table app that Dr. Falconberry made is a long time ago, not really that long ago, back when I was an undergrad, before Dr. Falconberry made that very cool app. You had to use like a distribution table that was in the back of a really big textbook. So I just wanted to show you what that looks like. What screen is that on? Here it is. Look, and so there would be something like this in the back of your textbook, and you can see like lower tail, upper tail, some portion, one standard deviation here. And so you'd have to figure out what your answer was using this table and these proportions here. And so you'd like search through it and you'd figure out which one you wanted. And so it's very interesting. Look, we can find three standard deviations, 99.8, well, 0.998, because there's a 99% chance you're within three standard deviations of the mean, right? And so that's what you used to use. You could also use some calculus to figure that out, but assuming you haven't taken calculus or remember how to do that in calculus, you wouldn't do that. So I will stop my screen share and that is it. And I'll post a video working through some problems with you soon, but this is enough for now.